So we're doing permutations and combinations. The first question, 9 cards, each of a different color, are to be arranged in a line. How many different arrangements of the 9 cards are possible? So part 1, there are 9 cards and they have to be arranged, means that permutations will be used. So 9p9 or 9 factorial, which will give 3628880. Part 2, the 9 cards include a pink card and a green card. How many different arrangements do not have the pink card next to the green card? So if there are 9 cards, so the pink card and the green card do not have to be together. So what we can do is that we can take the pink card and the green card together and then subtract the probability of the pink and green card being together from the total probability. So let's suppose the pink card was here, green card was here. So the arrangements of the pink and green card would be 2 factorial. And the arrangement of all the cards would be 1, 2, 3. This is taken as 1. So 4, 5, 6, 7, 8. 8 factorial. So 8 factorial times 2 factorial. And we'll subtract this from the total probability. So 9 factorial minus this. This will give the probability of the pink and green card not being next to each other. This is 282240. Next part, they're saying consider all possible choices of 3 cards. Now we're taking 3 cards from the 9 cards, and the 3 cards have to be arranged. How many different arrangements in total of 3 cards are possible? So out of 9 cards, we have to choose 3 cards and arrange them. So there are 2 methods for this. One could be directly arranging 3 cards from the 9 cards, or you could first choose 3 cards and then arrange them. These will both give 504. Now part 4, how many of the arrangements of 3 cards in part 3 contain the pink card? Okay. So we were selecting 3 cards from the 9 cards, but for the fourth part, the pink card has to be selected. So we have selected the pink card 1C1, we've selected the pink card, then we have 8 remaining, and from those 8 we can select any 2 cards. This was the selection of the 3 cards now, including the pink card. Now to arrange them, we'll multiply this with 3 factorial. So this gives 168. Now the last part, how many of the arrangements of 3 cards in part 3 do not have the pink card next to the green card? Again, over here I'll take the case where the pink card is next to the green card and then subtract that from the total probability of the 3 cards. So first selecting the pink card and the green card. So for the pink card 1C1, then for the green card 1C1. Now 7 cards remain, and from them we can select any 1 card, so 7C1. This was the selection. Now to arrange them, so there are basically 3 cards and we need the pink and green together. So if I take this as a sofa, this is 1 and this is 2. So the total arrangement will be 2 factorial, and then arrangement of the pink and green card will be 2 factorial. So to get my answer of the pink card being next to the green card, that will be 7C1 times 2 factorial times 2 factorial. This is equal to 28. This is the unfavorable possibilities, that is of the pink card being with the green card, whereas we needed the number of arrangements where the pink card is not next to the green card. So we'll subtract this from the total permutations, that was 504. So 504 minus 28 is equals to 476. Next question. In a sweet shop, 5 identical packets of toffees, 4 identical packets of fruit gums, and 9 identical packets of chocolates are arranged in a line on a shelf. Arranged. Find the number of different arrangements of the packets that are possible if the packets of chocolates are kept together. Okay. One more thing to note over here is that the packets of toffees are all identical, packets of fruit gums are all identical, and packets of chocolates are all identical. So they're saying that the chocolates are kept together, so we'll form a sofa of the chocolates. All 9 chocolates are together. These are the chocolates. Apart from that, there are 5 toffees and 4 fruit gums. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now how do we determine the arrangements? So total there are 1, 2, 3, 4, 5. We consider this as 1 to 6, 7, 8, 9, 10. 10 objects. So 10 factorial for that. Now the toffees are all identical. So to avoid repetition, we'll divide this by 5 factorial. And then again the fruit gums are all identical, so to avoid repetition we'll divide it by 4 factorial again. And because these are all identical, so we cannot arrange them, as arranging them will give the same order as they're all identical. So this will be the final answer, that is 1260. Part B. Jessica buys 8 different packets of biscuits. She then chooses 4 of these packets. How many different choices are possible if the order in which Jessica chooses the 4 packets is taken into account? So the order is being taken into account. So we'll first choose and then we'll arrange them. So out of 8, she's choosing 4 packets. So 8C4. And then she's arranging those 4 packets, so times 4 factorial, this will be 1680. This was B1. The 8 packets include 1 packet of chocolate biscuits and 1 packet of custard creams. How many different choices are possible if the order in which Jessica chooses the 4 packets is taken into account and the packet of chocolate biscuits and the packet of custard creams are both chosen? So again she has to choose 4 from the 8, but she must choose the chocolate biscuit packet and the custard creams packet. So to select the chocolate biscuit packet, because she has to choose it, so that will be 1C1. For custard creams again 1C1. Then out of the remaining 6, she has to select any 2 and then arrange them all. So 4 factorial. This will be 360. Part C. 9 different fruit pies are to be divided between 3 people so that each person gets an odd number of pies. Find the number of ways this can be done. So there are 9 different fruit pies. And every person has to get 3 people have to get the fruit pies, and every person should get an odd number. So the possibilities are that every person gets 3 fruit pies, or one person gets 5, the other gets 3, the third gets 1, or one person gets 7, the next gets 1, and the last gets 1. These are the 3 possibilities. Now if every person is getting 3, so how will we divide that? So there are 9 for the first person, out of that we're selecting 3. For the second, out of 6 we're selecting 3, and for the third, out of 3 we're selecting 3. So this is for 333, and there can't be any other possibilities because all of them are getting 3. When it's 531, so the first person is getting 5 out of 9, then 3 out of 4, and then 1 out of 1. over here it is possible that the first person gets 1 or the second person gets 1 or the first person gets 3 or the last person gets 3. So to find those arrangements, we'll multiply this by 3 factorial because there are 3 of them, so it's 3 factorial. For the last one, the first person gets 7 out of 9, then 1 out of 2, and then 1 out of 1. Over here again we'll have to arrange because they're not all identical, so it will be 3 factorial upon, because 1 is being repeated, so upon 2 factorial. The first one is coming equal to 1680. Second one is coming equal to 3024, and third one is coming equal to 216. So if you add them all, you'll get 4920, which is the final answer. So the next question: in a certain hotel, the lock on the door to each room can be opened by inserting a key card. The key card can be inserted only one way around. The card has a pattern of holes punched in it. The card has 4 columns, and each column can have either 1 hole, 2 holes, 3 holes, or 4 holes punched in it. Each column has 8 different positions for holes, and the diagram illustrates one particular key card. Okay. Now in the first part they're saying show that the number of different ways in which a column could have exactly 2 holes is 28. So in each column there are 8 possibilities, and out of those 2 holes have to be selected. So for the first part the answer will be 8C2, that is equal to 28. Second part, find how many different patterns of holes can be punched in a column. So in a column it's given that there can be 1 hole, 2 holes, 3 holes, or 4 holes. So for 1 hole the possibilities are 8C1. For 2 holes, as we did over here, the possibilities are 8C2. So I will add them. We'll add the possibilities to find total possibilities. Then for 3 holes the possibilities are 8C3. For 4 holes the possibilities are 8C4. This will give 162. In the last part, how many different possible key cards are there? So this is a little tricky. So we know that from the second part, we know that each column can have 162 different arrangements. So if each column can have 162 different arrangements and there are total 4 columns, so all the possible arrangements will be 162 times 162 times 162, third column, and then the fourth column 162. Since there are 162 possibilities in each column, so we'll multiply that 4 times, which is equals to 162 power 4. This is equal to 688 747 536. Question 4. Find how many numbers between 5000 and 6000 can be formed from the digits 1, 2, 3, 4, 5 and 6 if no digits are repeated. So in the first part there are no repetitions and numbers have to be between 5000 and 6000. So it's a 4-digit number. Now to be between 5000 and 6000, the first digit has to be 5. So to select 5, there is one possibility. The next number can be any one of the 6 except for 5. So there are total 6 numbers, so 5 cannot be there. So out of 5, we can select any one. For the next one, out of 4, we can select any one. For the last one, out of 3, we can select any one. So 5 times 4 times 3, this is equal to 60. Now part 2. In part 2, digits can be repeated. So again, a 4-digit number. The first digit has to be 5, so that it's between 5000 and 6000. After that, for the next digit, since the digits can be repeated, it can be any digits of the 6. So 6c1, then again 6c1, and then again 6c1. So it's basically 6 cube, that is equal to 216. Right, B, find the number of ways of choosing a school team of 5 pupils from 6 boys and 8 girls if there are more girls than boys in the team. We have to select 5 and there have to be more girls than boys in the team. So it's possible that there are 5 girls and 0 boys, or 4 girls and 1 boy, or 3 girls and 2 boys. If we have 2 girls, then the number of boys will be more than the girls, so that's not possible. So for the first one, out of 8 girls, there are 5 girls selected, so 8c5. Out of 6 boys, 0 are selected. Then for the second one, out of 8, 4 girls are selected, and out of 6, 1 boy is selected. Or the third, out of 8, 3 girls are selected, and out of 6, 2 boys are selected. This is 56, 420, 840. Now adding them all up gives us 1316. That was B1. Now B2. If 3 of the boys are cousins and are either all in the team or all not in the team. So there were 14 people in total in the beginning, 6 boys and 8 girls. Out of those 14, 3 are cousins and 11 are the others. So either all of them get selected or none of them get selected. So the possibilities are that all of them get selected. So if 3 are getting selected from here, so we need a total of 5. So from the rest of the 11, there should be 2. The second possibility is that none of them get selected, so 3c0, and all of them get selected from the 11. So this is equal to question 5. The first part, a chess team of 2 girls and 2 boys is to be chosen from 7 girls and 6 boys in the chess club. Find the number of ways this can be done if 2 of the girls are twins and are either both in the team or both not in the team. Part A. First, let's take the scenario where both the twins are in the team. So for the boys, out of 6, 2 will be selected. Now for the girls, if both the twins are in the team, so out of the 2 twins, both the twins are selected. From the remaining 5 girls, 0 gets selected. Plus, if the twins are not in the team, then again for boys, out of 6, 2 are selected. For the twins, none of the 2 are selected, and from the rest of the 5 girls, 2 are selected. So this will give 165. Part B, the digits of the number 1, 2, 4, 4, 6, 8, 7 can be rearranged to give many different 7-digit numbers. How many of these 7-digit numbers are even? So if the 7-digit numbers have to be even, then they should end in 2, 4, 4, 6 or 8. So I'll take 2 scenarios. The first one is that it ends in 2, 4, 2, 6 or 8. So in that case, there's a 7-digit number. The last digit has 3 possibilities, 2, 6 or 8. So 3c1. For the rest of the 6 digits, we can arrange them using 6 factorial, but because there are two 4s, so to avoid repetition, we'll divide it by 2 factorial. This was the first case where we take 2, 6, 8 as the last digit. Now if we take 4 as the last digit, the last digit has one possibility, and the rest of the 6 digits can be arranged using 6 factorial because over here there is no repetition. So for the total answer, we'll have 6 factorial upon 2 factorial times 3 3c1 is 3 plus 6 factorial. So this will be equal to 1800. B2, how many different numbers between 20,000 and 30,000 can be formed using 5 different digits from the digits 1, 2, 4, 6, 7, 8. So this is a 5-digit number now. The first digit has to be 2 so that it's between 20,000 and 30,000. So for the first digit, the possibilities are 1c1. After that, there have to be 5, all the digits have to be different. So if 2 is gone, we have 1, 2, 3, 4, 5 more possibilities. So for this second digit, we have 5 possibilities. For the next one, we have 4. For the next, we have 3 and then 2. So it's 5 into 4 into 3 into 2. That is equal to 120. In the last part, Helen has some black tiles, some white tiles and some grey tiles. She places a single row of 8 tiles above her wash basin. Each tile she places is equally likely to be black, white or grey. Find the probability. Okay, so they're asking for the probability that there are no tiles of the same color next to each other. So there has to be a line of 8 tiles and no 2 tiles next to each other should be the same color. So for the first tile, we'll have 3 possibilities, that is black, white or grey. Now if one tile has been selected, for example black, then for the second one we have 2 possibilities, that is white or grey. Again, one is selected over here, for example grey. So for the next one we have black and white, 2 possibilities. So it will keep going on as 2 possibilities for each next tile. Right, so this is going to be 3 times 2 power 7. This is the favorable outcomes की possibilities. Now for the total outcomes, the possibilities will be that there are 3 for the first one, 3 for the second one, 3 for the third one, and so on. So this will be equals to 3 power 8. Now for the probability, we'll divide the favorable outcomes by the total outcomes. This gives us 0.0585. Question 6. The 11 letters of the word remembrance are arranged in a line. Find the number of different arrangements if there are no restrictions. So there are 11 letters, so 11 factorial, and to remove the repetitions, we'll divide by 2 factorial for the 2 R's, 3 factorial for the 3 E's, and 2 factorial for the 2 M's. So this will be 166 3200. Second part, find the number of different arrangements which start and finish with the letter M. So there are 11 letters. The first and last should be M. So for M, it's going to be 2C2. Then for the other 9 letters, it's going to be 9 factorial upon 2 factorial for the 2 R's and 3 factorial for the 3 E's. This will be 30240. Third part, find the number of different arrangements which do not have all 4 vowels next to each other. So we'll take we'll use the sofa method over here. We'll take the 4 vowels together, and then we'll subtract that from the total possibilities. So if these are the 4 vowels, so this will be the arrangement of the 4 vowels will be 4 factorial upon 3 factorial for the 3 e's. Then there are 1, 2, 3, 4, 5, 6, 7, 8. 8 total digits. So 8 factorial upon, for the repetition of the m's and r's, so 2 factorial into 2 factorial, because these will contain the m's and r's, times the arrangement of the sofa. This will be equal to, this is when the vowels are together. We'll subtract this from the total that we found in the first part, 1663200, 1663200 minus 40320. This is equal to 1622880. So I'll go over this again. I took the 11 digits, boxed 4 of them in the sofa. These are the vowels. The arrangement of the vowels will be 4 factorial upon 3 factorial, because the vowels are E, E, A, E. So there are 3 E's. To avoid repetition, we'll divide by 3 factorial. Now there are 1, 2, 3, 4, 5, 6, 7, 8 total digits. So 8 factorial. And in these there are 2 m's and 2 r's. So 2 factorial into 2 factorial. Times is the arrangement of this. So we got 40320. That is the arrangement with the vowels together. We'll subtract that from the total arrangements to find arrangements of the vowels not being next to each other. In the fourth part, it's saying 4 letters from the letters of the word remembrance are chosen. Find the number of different selections which contain no m's, no r's, and at least 2 e's. So 4 letters have to be selected, and the most important thing over here was that it's saying that different selections, so we won't arrange them, we'll only select them. So there have to be 2 e's or 3 e's, at least 2 e's, so 2 e's or 3 e's. So if there are 2 e's and there don't have to be any m's or r's, so no m's, no r's. So apart from the e's, there are 1, B, A, N, C. There are 4 other letters. So we got 2 e's, and from the other 4 letters we'll select 2. So 4C2 into 1 will be 6. Or the second possibility, that is there are 3 e's. We'll have 3 e's, and then for the last one out of 4 we can select 1. So 4. So 6 plus 4 equals 10. These are the different selections which contain no m's, no r's, and at least 2 e's. Question 7. A small aeroplane has 14 seats for passengers. The seats are arranged in 4 rows of 3 seats and a back row of 2 seats. 12 passengers board the aeroplane. How many possible seating arrangements are there for the 12 passengers? Give your answer correct to 3 significant figures. So in the first part, they're saying that we have to find the possible seating arrangement for the 12 passengers. There are 14 seats and 12 passengers, and they're saying arrangements, so 14p12. This is going to be equal to 3 significant figures. It's going to be equal to 4.36 times 10 power 10. Second part, these 12 passengers consist of 2 married couples, 5 students, and 3 business people. The 3 business people sit in the front row. So the 3 business people sit in the front row. So for the business people, it's going to be 3p3, because there are 3 possibilities and there are 3 people. Then the 5 students each sit in a window seat. Mr. and Mrs. Lynn sit in the same row on the same side of the aisle. Mr. and Mrs. Brown sit in another row on the same side of the aisle. How many possible seating arrangements are there? So they're saying that the couples have to sit together on the same side of the aisle. So either the couples will sit over here or here or here. So for the couples, there are 3 possibilities, right? 3p2. Out of these 3 places, the couples will take 2 places. So 3p2. Now if, for example, Mr. and Mrs. Lynn sit over here, there are two possibilities of that Mr. Lin sits here, Mrs. Lin sits here, or Mr. Lin sits here and Mrs. Lin sits here. So we'll multiply it by 2 factorial for Mr. and Mrs. Lin, and then 2 factorial for Mr. and Mrs. Brown. This was for the couples. Now the 5 students are left. So if, for example, and the 5 students have to sit at a window seat. So if, for example, Mr. and Mrs. Lin got this seat and Mr. and Mrs. Brown got this seat, so for the students there is 1, 2, 3, 4, 5 possible seats, and there are 5 students. So that will be 5 factorial. So this is equal to 17280. In the last part, part 3, they are saying that if instead the 12 passengers are seated randomly, find the probability, which is the probability that Mrs. Lin sits directly behind the student and Mrs. Brown sits in the front row. So Mrs. Brown has to sit in the front row, means these 3 places, one of these 3 places. So for Mrs. Brown, I'll write 3p1, because from these 3 she has to sit at one place. Then Mrs. Lin sits directly behind a student. So where can Mrs. Lin sit so that a student can sit in front of her? So in one of these places there's Mrs. Lin. For example, if Mrs. Lin is over here, so Mrs. Brown is over here. So Mrs. Lin can sit over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In these 10 places Mrs. Lin can sit so that there is a space in front of her for the student to sit. If she sat over here, then the student couldn't sit over here, so that's why we won't consider this. So for Mrs. Lin there are 10 places, 10p1. Now for example, Mrs. Lin sat over here and she has to sit directly behind a student. So the student has to come over here, and there are 5 students. So there are 5 possibilities, 5 students to select from, and we have to select one student. So it will be 5c1. Now 3 people have been selected out of the total 12, so 9 people remain, and 3 places have been used, so 11 places remain. So 9 people have to be seated in 11 places, so 11p9. Now because you have to find the probability, so we'll divide by the total outcomes, that is 14p12. This is equal to 0.0687.